Hello and welcome to TutorTube, where the Learning Center's lead tutors help you understand challenging course concepts with easy-to-understand videos. My name is Ethan, lead tutor for biology and chemistry. In today's video, we'll explore moles and stoichiometry. Let's get started. A mole is nothing but a certain number of something. We call it Avogadro's number. Just like a dozen is 12 of something, a mole is 6.022 times 10 to the 23rd of something. It has been defined to mean that number. Therefore, if I have 1 mole of eggs, that means I have 6.022 times 10 to the 23rd eggs. Just like if I have a dozen eggs, that means I have 12 eggs. The purpose of the mole is to bridge the gap between the macro world and the micro world. For example, we can represent 5 grams of iron in terms of the number of moles. We simply divide the 5 grams by the molar mass of iron. Molar mass is defined as the number of grams in 1 mole of a given element. Iron has a molar mass of 55.84 grams per mole. So 5 grams divided by 55.84 grams per mole gives us 0.089 moles of iron. Here we can see the practicality of using moles. If we were to represent 5 grams of iron in terms of the number of atoms of iron, we would get 5.3 times 10 to the 22 atoms. A much more cumbersome number to work with. Basically, we use moles to be able to represent the number of atoms and molecules with a smaller, easier to work with number. Like I said before, each element has a specific molar mass. That is, 1 mole of an element weighs X number of grams. This is based on its atomic weight. Here we see iron, hydrogen, and carbon. 1 atom of hydrogen is smaller than 1 atom of iron. Therefore, hydrogen weighs less and has a smaller molar mass than iron. You can get the molar mass of any element from the periodic table. So, we understand the molar mass of individual elements, but what about finding the molar mass of a compound? Well, to find the molar mass of a compound, you simply just add up the molar masses of the individual elements that make up that compound. For example, say we want to find the molar mass of Fe2O3. We take the molar mass of iron and multiply it by 2. Then we take the molar mass of oxygen and multiply it by 3. Finally, we add those two products together. For iron, that's 55.84 grams per mole times 2, since we have 2 atoms of iron in each molecule of Fe2O3. For oxygen, that's 15.99 grams per mole times 3, since we have 3 atoms of oxygen in each molecule of Fe2O3. Once we add those together, we get the molar mass of Fe2O3 to be 159.65 grams per mole. We can also use moles to find the mass of a single atom of a given element. Say we wanted to find the mass of 1 atom of carbon. We would start with the molar mass of carbon, which is 12.011 grams per mole. Then we divide by the number of atoms in 1 mole, which is 6.022 times 10 to the 23rd. And we get 1.99 times 10 to the negative 23rd grams for 1 atom of carbon. It's important to pay attention to the units here. Whenever we're doing conversions like this, we want to think about what units we want to get rid of and what units we want to end up with. We're starting with grams per mole, which is molar mass, but we want to end up with the number of grams per atom. Therefore, we put 1 mole in the numerator of our conversion factor to cancel out the moles found in the denominator of the previous term. In the end, we're left with grams per atom just like we wanted. Anytime we're using moles, it's going to be involved in some conversion of units. The question might ask, how many moles are present in 5 kilograms of gold? To find out, we start with 5 kilograms of gold, and then we multiply by 1,000 to convert to grams. Then we divide by the molar mass of gold, which is 196.966 grams per mole, as found on the periodic table. Finally, we get that 5 kilograms of gold contains 25.38 moles of gold. Again, pay attention to which units are canceling out and which remain in our final answer. We have kilograms on the top and bottom, so those cancel. And we have grams on the top and bottom, so those cancel. That leaves us with moles. Using moles is especially important when predicting how much product a reaction will produce. For example, if you were given 5 grams of tricalcium phosphate, 10 grams of carbon, and 7 grams of silicon dioxide, we can predict how many grams of calcium silicate you can produce. Tricalcium phosphate is Ca3PO42, silicon dioxide is SiO2, carbon is C, and calcium silicate is CaSiO3. Since the mass of different compounds vary, we cannot only base the reaction on how many grams we have. We have to make comparisons on a molecule by molecule basis, and we can do this using moles. If we take each mass that we're given and divide by the molar mass, we get the number of moles. For Ca3PO42, the molar mass is 310.18 grams per mole. Then the 5 grams that we were given divided by 310.18 gives 0.016 moles of Ca3PO42. We apply the same logic for carbon and SiO2 to get 0.83 moles of carbon and 0.11 moles of SiO2, while making sure to use each molecule's respective molar mass. Now that we have the number of moles of each compound, we need to determine which reagent is the limiting one. The limiting reagent is the reagent we have the least of and will therefore determine how much product we can make. For any reaction, it will only occur in the ratio of the balanced equation. So in order to determine the limiting reagent, we need to multiply the number of moles that we have for each compound by the stoichiometric coefficient that it has in the balanced equation. For Ca3PO42, that's 0.016 moles times the coefficient of 2, which equals 0.032. For carbon, we multiply 0.83 by 10 to get 8.3. Finally, for SiO2, we multiply 0.11 by 6 to get 0.66. And since Ca3PO42 has the smallest number, it's the limiting reagent. So our final step is determining the amount of product we'll produce based on our limiting reagent. So given the original number of moles, which was 0.016, we multiply by the ratio of Ca3PO42 and our product, which is CaSiO3. In our balanced equation, we have 2 moles of Ca3PO42 for every 6 moles of CaSiO3. Then we multiply by the molar mass of CaSiO3 to give 8.27 grams of CaSiO3. Again, it's important to recognize where we placed each of our units for each of the conversion factors. When we multiply 0.016 moles of Ca3PO42 by 6 over 2, we put the 2 on the bottom because it has the units of Ca3PO42, which cancels with the units of our first term. Then we multiply by the molar mass of CaSiO3 because that cancels out our moles of CaSiO3. And in the end, we're left with grams of CaSiO3, just like we want. The following reference is for the images used in this video. Thanks for watching TutorTube. I hope you enjoyed this video. Please subscribe to our channel for more exciting videos. Check out the links in the description below for more information about the Learning Center and follow us on social media. See you next time.